$250 million and 7,000 kilometers. And after you bury your investment at the bottom of the Atlantic Ocean, you still haven't solved the hardest problem, making money from it. Because owning an undersea internet cable sounds like owning the ultimate digital toll road. The world needs the internet needs cables, and you own one of them. So every byte crossing the ocean should make you richer, right? Not exactly, because internet traffic can explode while the price of moving that traffic falls. Your $250 million cable can be damaged by something as ordinary as a fishing vessel. And your biggest competitor might not even need to make a profit from its cable, because its biggest customer might actually be itself. So if you actually wanted to own one of the machines carrying the world's digital economy, what would you really be buying? And could it actually make you rich? To find out, we first need to spend a few $100 million. First, you need the cable, but you can't simply manufacture one and throw it into the ocean before anything touches the water. You need to know exactly where it will go. Engineers begin by studying the seabed. They map a route between continents. They look for underwater hazards. They study water depth. They identify dangerous terrain. And they examine areas with heavy maritime activity. Then comes regulation. You need permits. You need landing rights. You need environmental approvals. And you need permission to connect the cable to shore. Only then can construction truly begin. And this is where the numbers become enormous. The cable component alone can cost roughly $6,000 to $20,000 per kilometer. Now stretch that cable across the Atlantic. A representative 7,000-kilometer transatlantic system could cost around $250 million. Cross the Pacific, and the price can approach $400 million. But you're not buying one giant wire. Inside are incredibly thin strands of optical fiber. Those fibers carry data using pulses of light. Modern systems can contain many fiber pairs, but those signals have to travel thousands of kilometers. So repeaters are installed along the route. They keep the signal moving across the ocean. Then you need a specialized cable-laying ship. The cable is loaded onto the vessel. The ship slowly follows the planned route, and kilometer by kilometer, your investment disappears beneath the ocean. Near coastlines, the danger increases. Fishing activity is heavier. Ships drop anchors. So vulnerable sections may need additional protection. Some sections can even be buried beneath the seabed. Eventually, the cable reaches land, but the spending still isn't over. You need landing infrastructure. You need terminal equipment. You need power. You need terrestrial network connections. And most importantly, you need something valuable at the other end. Data centers, cloud infrastructure, telecom networks. Internet exchanges businesses because a cable connecting two random beaches isn't worth $250 million. The cable needs to connect demand. This creates the first brutal rule of cable economics. You can build an incredible amount of capacity, but if nobody needs your route, you've built a highway with no traffic. Here's where ownership gets strange. Imagine an empty 8-lane highway. One company controls 2 lanes, another company controls 2 more, and a third controls the rest. Something similar can happen beneath the ocean. One physical cable can serve multiple owners. Different companies can control different fiber resources. Others can secure long-term rights to capacity. Take the transatlantic cable known as Maria. It connects Virginia Beach in the United States to Bilbao in Spain. The project involved major companies including Meta, Microsoft, and Telxius. Different participants obtained rights to parts of the system's infrastructure. The name sounds complicated. The idea is simpler. You don't necessarily need to build the entire highway. You can secure long-term rights to use part of it. For the buyer, that provides long-term network capacity. For the cable owner, who provides something equally important, committed demand, and potentially money before the cable reaches full commercial maturity. This is why consortium ownership can make so much sense. Imagine 4 companies need enormous capacity across the Atlantic. Each could build its own cable, or they could share one enormous construction project. They divide the cost, they divide the infrastructure, and they divide the fiber. Companies that compete everywhere else can cooperate beneath the ocean, because financially cooperation can be cheaper. So the real question isn't simply centrish, can you afford an undersea cable? How much of one do you actually need? But eventually somebody has to pay for all of this. Which brings us to the real business. What exactly are you selling? Because the answer isn't through the internet. An undersea cable doesn't create the internet. It moves data between networks. So what you're really selling is Nesco capacity. That capacity can be packaged in different ways. You can sell long-term capacity agreements. You can provide wholesale connectivity. You can sell wavelength services, or companies can control dedicated fiber resources. Your customers might be telecom companies, internet service providers, cloud providers, technology companies, governments, or other network operators. Depending on your infrastructure, there can also be economics around landing stations, colocation, cross-connects power, interconnection, but the fundamental economics remain the same. You spend an enormous amount upfront, then you wait. Construction can be delayed. Permits can take longer than expected. Financing can become difficult. And until the system enters service, your expensive new asset isn't carrying profitable traffic. Now imagine our hypothetical cable costs $300 million. You finance part of it with equity, and you borrow another $20 million, new $5 million at an illustrative 7% over 15 years. Annual debt service alone would be around $13 million new fighters every year. Whether your cable is full or empty, whether customers arrive or not, the bank doesn't care how impressive your engineering is. It wants its money, and this creates enormous operating leverage. If your cable attracts heavy utilization, the economics can become extremely attractive because the infrastructure is already there. You don't need to build another Atlantic Ocean. Every time a customer arrives, unsued capacity can become monetized capacity. But operating leverage works both ways. A busy cable can be powerful. An empty cable can be financially terrifying. And there's another problem. The world can use more internet every year while your capacity becomes less valuable per unit. More streaming, more cloud computing, more digital services, more AI infrastructure, more data moving between continents. You might assume cable owners automatically become richer, but technology keeps improving. Existing systems become more efficient. New cables add more supply. Competition increases, and the price of transporting each unit of data can fall. So you can carry more bits and still earn less per bit. That's the bandwidth paradox. More internet traffic doesn't automatically mean more profit. Theoretical capacity isn't what matters. Most economically useful capacity is. Imagine spending hundreds of millions of dollars by test on an undersea cable, but instead of asking Tor, who can we sell this capacity to? Historically, the business model was relatively straightforward. Telecommunications companies built international infrastructure, then they sold telecommunications capacity, but the internet changed. Cloud computing exploded. Video streaming grew, social media became global. Data centers multiplied, and technology companies started moving enormous amounts of data, not just between users, but between their own infrastructure. Companies like Google, Meta, Microsoft, and Amazon, they weren't simply customers of the internet anymore. They had become some of its biggest traffic generators, and that changed the economics. Imagine you're a traditional cable company. You spend $300 million. Now you need customers. You need companies willing to buy your capacity, and you need them to pay enough. Otherwise, your investment fails. But imagine you're a hyperscale technology company. You already have users. You already have cloud customers. You already operate data centers. You already move enormous amounts of information. And most importantly, you already know demand exists. Now the cable doesn't have to make money in the traditional way. It can create value somewhere else. Maybe it reduces your dependence on third-party networks. Maybe it gives you greater control over your infrastructure. Maybe it creates a more direct route. Maybe it improves resilience. Maybe it connects your data centers more efficiently. And maybe it supports businesses worth far more than the cable itself. Cloud computing, digital advertising, streaming AI infrastructure, online platforms. Suddenly, asking how much revenue the cable generates can miss the point. The cable may create enormous economic value without producing conventional cable revenue. Think about a giant retailer. It builds a massive warehouse. The warehouse doesn't sell tickets at the entrance. Customers never pay to visit it, but the warehouse still creates enormous economic value because it makes everything around it work. An undersea cable can operate on a similar principle. For a hyperscaler, the cable isn't necessarily the product. The cable supports the product, and its biggest customer can effectively be itself. That's an enormous advantage. A traditional owner may need to find demand. A hyperscaler can bring demand with it. The cable isn't searching for a purpose. The purpose already exists, and this may be the single biggest advantage in the entire industry. Demand certainty, but even guaranteed demand can't protect you from everything because your $250 million investment is about to spend the next 2 decades at the bottom of the ocean. What is the biggest threat to an undersea internet cable? You might imagine sabotage, a hostile government, an underwater attack, or some sophisticated cyber operation. But the most common danger is much more ordinary fishing and ship anchors. Roughly 150 to 200 submarine telecom cable faults occur globally each year, and around 70 to 80% are caused by accidental human activity, especially fishing and anchoring. Imagine a vessel moving near the coast. Nothing unusual, nothing dramatic. Its anchor reaches the seabed. Then it begins to drag. The anchor catches something, a cable. Suddenly, your $250 million infrastructure has a fault. Now you need to locate the damage. A specialized repair vessel may need to mobilize. Permits may be required. Weather matters. Location matters. The damaged cable has to be recovered. The broken section has to be repaired. Then it has to be tested. And finally returned to service. Repairs can reach 7 figures, but the repair bill itself may not be your biggest problem. Time matters too. Industry repair data presented in 2026 showed an average of about 23.4 days from fault notification to repair vessel departure. But that doesn't necessarily mean 23 days without internet. Modern networks can reroute traffic, and that depends on something incredibly valuable. Redundancy. Imagine you own only one route. A fault hits your cable. You have a serious problem. Now imagine you control capacity across multiple routes. One cable fails. Traffic moves elsewhere. The problem doesn't disappear, but your network survives it. And this reveals another advantage of scale. One cable is an asset. Multiple cables become a network. And a network can be more valuable than the sum of its individual cables. But there's an even worse scenario than your cable breaking. Imagine the cable works perfectly and nobody wants it. You commit the $300 million. Construction begins. Then the project gets delayed. Costs accumulate. While you're waiting, a competing cable launches. It has strong financial backing, it has better connections, and it already has customers. Your biggest potential customer chooses the competitor. Your cable finally enters service, but utilization is far below expectations. So you lower prices. That attracts some demand. But now, each unit of capacity earns less. Debt payments continue. Operating costs continue. Maintenance costs continue. Then a fault occurs. You need repairs. Cash flow gets tighter. So you discount capacity again. Margins weaken. Investors become nervous. Refinancing becomes harder. Eventually, you need more capital. But nobody wants to put more money into an underperforming asset. The cable might be technologically impressive. It might carry enormous amounts of data. It might work exactly as designed. And financially, it can still fail. Because the nightmare isn't that your cable breaks. It's that nobody needs your cable badly enough to pay the price. Your financial model assumed internet growth alone isn't an investment thesis. Demand has to exist on your route, at your landing points, at a price that makes the economics work. So reason who actually wins. The ideal owner doesn't begin with a cable. It begins with demand. Maybe you're a telecom carrier with customers already committed. Maybe you're part of a consortium sharing the construction cost. Or maybe you're a hyperscaler with enormous internal traffic moving between data centers. Then comes geography. Where does your cable land? What's waiting there? A major city, a data center cluster, an internet exchange, or almost nothing because crossing the ocean is only part of the journey as data still has to travel inland. It needs terrestrial networks, it needs data centers, it needs connections to other networks. This means the landing point can matter almost as much as the cable itself. Then comes redundancy. One cable gives you one concentrated bet. 2 cables give you an alternative. More cables create multiple routes, and eventually you don't own a cable anymore. You own a network. That's the final shift. The real asset isn't simply the line under the water, it's the entire system surrounding it. The route, the landing stations, the terrestrial connections, the data centers, the customers, the demand, and eventually, the network. So would owning an undersea internet cable make you rich? Possibly. But not simply because you own a cable. For a telecom carrier with contracted demand, it can become a powerful long-term infrastructure business. For a consortium, sharing hundreds of millions in construction costs can make an otherwise impossible project rational. And for a hyperscaler, the economics can become even more interesting, because the return doesn't have to stop at bandwidth sales. The cable can support data centers, cloud computing, AI infrastructure, content delivery, and businesses worth far more than the cable itself. But for a speculative investor, with no customers, no internal traffic, and no operating expertise, this can be an extraordinarily dangerous place to put hundreds of millions of dollars, because the most expensive problem isn't necessarily a broken cable, it's an empty one. A repair costing millions can hurt, but a $300 million sumper asset without enough economically valuable demand can be far worse, and that's the contradiction hidden beneath the ocean. The world absolutely needs undersea internet cables, but that doesn't mean the world needs yours. The winners aren't simply the companies that can afford to build them. They're the companies that already know exactly why the cable needs to exist, because ultimately, the real business isn't owning thousands of kilometers of fiber. At the bottom of the ocean, it's controlling the demand, the route, the capacity, the connections, and the network surrounding it. The cable is just the physical link. The real asset is everything it connects.